Hi. Imagine you're the owner of a store and you need to make an important call. Let's say it will roughly take 10 minutes. Well, you might then be interested in the probability that you have at least 10 minutes between having to serve arriving customers. From week 2, you probably remember that the number of customers arriving at the store per hour can be modeled by a Poisson distribution with some parameter lambda. In this sketch, we would have n as the number of customers equal to 3. Now, the waiting time between customers is clearly a continuous random variable. Let's call it x. X can be modeled by a random variable with this probability density function. And the parameter lambda is the same as in the Poisson random variable. Now, notice that the density is 0 for negative x, which makes sense, right? The waiting time to the next customer cannot be negative. Also, you notice an exponential function there, which explains the name of this random variable. Feel free to pause the video and check that this is indeed a density function. It should be a non-negative function, and the area under the graph should be 1. As we did in the Poisson video, we will work with this formula first, and then we will go into more detail about where this density function comes from at the end of the video. Recall that the parameter lambda controls the expected number of arrivals over a given time interval. Accordingly, it has an inverse effect on the waiting times between these. A larger lambda corresponds to a larger expected number of customers, and therefore shorter waiting times. Any continuous random variable with a probability function of this form is said to follow an exponential distribution with parameter lambda. You know by now that it is sufficient to give the density function little f, because the distribution function capital F can easily be obtained by integration. Its expectation is given by 1 divided by lambda, and its variance by 1 divided by lambda square. You can find a proof of these two properties in the reading material after this video. The exponential distribution is applicable anytime that you're interested in the waiting time between events that are modeled by a Poisson distribution. Therefore, the same assumptions as with the Poisson distributions should be met. Occurrences take place instantaneously, individually, and independently at a constant rate. The time interval no longer plays a role here.